Thank you for this invitation, giving me the opportunity to talk about. Actually, this talk is based on what we are doing, and okay. I'm basically a climate scientist. It's not an AI or ML expert, but we use ML techniques just like any other statistical tool. Like I used to draw figures with IDL, for example, or MATLAB, or we use Python for programming, for example, like that. So these ML techniques also just like a tool for our research. So here we actually wanted to talk about application in climate science, but then I thought there will be talks regarding that. Then I thought there will be students. So how we can use the same techniques in some slightly different, like atmospheric physics and chemistry, is also very important in the first part, because all physics are going to the model. Otherwise, your model will not be working. And the chemistry is a new part. Actually, this is just starting, application of ML techniques in chemistry. People have just started working on that. So I just wanted to give you what we are doing and how you can apply this and what are the issues that we face and what you do or what you should not, okay? So you know that there are different techniques in machine learning itself, like supervised, unsupervised, semi-supervised reinforcement of learning. But technically, it's just like it's a subset of artificial intelligence that enables computers to learn from and make predictions, decisions based on the data. So the key thing is data here, okay? Whatever method you use, and that's also the buzzword, and you have machine learning, you have supervised learning. In supervised learning, you have weather forecasting, and you can also you can make classification, and reinforced, you have even game AIs, and unsupervised, you have structured discovery, and many other things. So in application in climate science, it's very important because it's huge volume of data you handle. So that's it. One of the biggest advantage of using ML techniques are a variety of data sets you can fuse, and you have high dimensional data sets. You can recognize the patterns, and you can also extract the features, and you can automate your programs or your models and increase the efficiency, and you can also integrate diverse data sets. And indeed, you can use the prediction models, like climate prediction or weather prediction, and you can also assimilated data. These days, it's very important assimilating data because for models, any dynamical models, you have to give a structured data set inside the model. So we were talking about measurements, right? He was talking about 350 stations are there, but these station data will not go there. You have to make a grid. You have to make a structure, and you have to make a grid, and then only you can feed that into model. So you can use that, and then again, you can use image classification, feature, and risk assessment like that. And you can also assess your pollution in the city. For example, Delhi, it's a big problem, pollution tracking and prediction. And then you can also predict floods, and many people are working on flood prediction models, particularly urban floods. And then the question is data source. What are the source of the data? And before going to that, the important thing is we need accurate and comprehensive data. So Sir was asking this question, whether you validate this data, how good are these data? We'll come to that point later. But data are the key. And then about the sources, you have different kind of sources, measurements. You have laboratory data. You have remote sensing data. For example, many satellites are there. You have historical data set. You have model data itself. For example, big climate models, you can, if measurements are not available, you can take model data. And then you can also have surveys, either geological or any other surveys. And then we have also problems or challenges here. But this slide, I will come to this slide later. But we can also do something about these challenges, like you can have advanced techniques in terms of use your machine learning technique, whatever that may be, but you add some another analytical method and play together. And then another way to handle this is manage your data. Now let's look at the application side. These are the case studies. These are the studies that we have done. So it's just like case studies. We start with this question, how the statistical relationships are analyzed. For example, this is application. Mainly, broadly, we have 3 applications. Okay, if I use one of these ML techniques, looking at whether to find a relationship between maybe there's 2 parameters, or 2 variables, or in physical terms, 2 processes, something happening there, and whether it affects here. For example, you are asking how outside temperature here. Okay, maybe today's temperature is 26 degrees, and whether this has any connection with yesterday's rainfall or today's rainfall. And how do we find it? Usually you have 2 sets of data. You find simple correlation. Usually we do that. And there are other methods. You can have multiple correlation or MLR, or you can have principal component analysis. You can use causal analysis. That's what we do these days. Okay? And you can also do trajectory analysis. When we were talking about Delhi pollution, for example, okay, we are also talking about some stubble burning outside the Delhi outskirts, and then whether it carries the pollution or not. It's also an attribution, right? Okay, the trajectory is coming. For example, the trajectory is coming from this side. So, okay, this side you have high pollution, so it is coming. All these air masses bringing those pollution to that city like that. So there are different ways to look at the statistical relation. So it's very important, this word. That's why I put that in red. Okay? Sometimes you can correlate any 2 matrices, right? These are just numbers for a program is there. For the program, both, whether this is temperature or relative humidity, for that program, it's just a set of 2 matrices, just numbers. We interpret, right? We interpret this is temperature, this is relative humidity. So these are statistical relationships. You should know what you are doing. Can we do this after the talk? Okay. And then, so we are talking about climate, and then we have this global warming problem. Whenever we talk about weather or climate, we start with temperature, right? Let's start with temperature here. So the temperature is, global warming is happening. That means the surface temperature is increasing in the world. But this temperature increase or the distribution is not uniform, or the temperature increase. The trend in temperature is not uniform because there are many other factors involving in it. So if global warming is happening or temperature in India is increasing, these are the results for India from our studies. I'm not reading that. So if we want to do something about it, okay, if there is a problem, then we need a solution, okay? So our problem is temperature increasing in India. We know that these are because of the emissions, okay? Anthropogenic emissions, for example, CO2, CH4, N2O, tropospheric ozone, these are the 4 important gases. So you know the problem and you want to solve it. So how to solve it? Then you need to know the drivers, right? What drives this increase? Or what drives the disparity from one region to the other? What is the reason for this? A cause. We need to find a cause. So one way to do that is, okay, you are talking about temperature, then you are finding, okay, temperature is changing from one region to the other, and you are looking, okay, what are the drivers or what are the parameters? You are saying that, okay, temperature is affecting rainfall. You say that. Okay, then you just start with any model, you just start with a simple regression equation. Y is equal to mx plus c can be constant or c.
Is it the temperatures are monthly temperature, seasonal temperature?
Anything you can take, sir. I am coming to that point. This t can be anything. You can regress it, even daily data. So when you start with any model, any simple model is a form of a small regression equation, y is equal to mx, c can be 0. That means you have to give a data first, right? X is the data you give and y you will get. And then you say that, okay, humidity is a factor, or today is humid, so we feel more temperature. Then you add m1 x1 plus one term is there. Then you are saying that not only humidity, there was rainfall, then you wanted to add rainfall function. Then there is another term comes, m1 x1 plus m2 x2. And then you are saying, no, there was clouds and there may be some sort of radiation interruption or something. You wanted to add the cloud term, then that is the term of m3 as a coefficient, and And so whatever you think, your model is your model, your thought. You think that, okay, temperature is only affected by humidity, then your model is just one function. But you can also add many of these. But we don't add everything. We think that the dominant factors, we think that these are mostly contributing, the others are insignificant. So the significant terms you add. So that's one aspect. And then you can also see one term here, ENSO. In climate science, these kind of functions work with large-scale circulation, for example. ENSO is El Nino Southern Oscillation. This is simply in simpler terms, if there is a change in surface temperature of sea in the Pacific, usually in November, December, those months, or January, and that could affect different climate patterns in different regions of the earth. Even in India also, it will affect. You might have read in newspapers that, okay, this year is El Nino, so you have warmer temperatures like that. Okay, it's one manifestation of that. So you could also add such kind of terms. And then you regress it. And then you regress it, and then you will find the contribution like this. These are the contributions written in different temperature homogeneous regions in India. Okay? So these numbers, and you can say that this is eastern coast, and this different, for example, Henso here, it's very small contribution here, but it's TP, that is the pressure, its contribution is different. So that means if you regress it and you do that for different regions, you will get a contribution of different function, and then you will find that, okay, in this region, humidity is affecting more, and the other region effect is different like that. So this is one way to attribute. This is one way to find the drivers. Okay? But here is a problem. Because these are linear. Nothing happens in linear outside, in the real world. So there are many non-linear complex processes, and then this correlation-based analysis or even the regression is not enough. It's insufficient. And it is particularly when there is another variable or a covariate is influencing both of this. So here comes the causal analysis, one of these ML techniques that we use to find the relationship among the drivers, not between 1 and 2, but among the drivers. Maybe X is affecting Y, but X is also affecting Z, and Z is affecting Y like that. So this is not possible with a linear analysis, linear regression. So in this particular work, we were using a PCMCI, causal analysis. And you know that it's initially it estimates the partial correlation between two time series, and then it finds the statistical significance of each of these correlation, and then there will be a number of tests will be performed, and you will look at the statistical significance. For example, you can define that. Two things you have control in it. One is the time delay. That means you are saying that this process will be affecting temperature in 1 month lag or 2 months lag. So you have control over that. The second thing is the significance threshold. For example, when you draw the causal relationships or the causal graph, you are taking only, for example, 95 CA. The confidence interval you are setting 95 or 2 sigma level, for example. You can also reduce it 85 or 90 up to it's up to you. So these two processes you have control, otherwise the other things will be taken care of PCMCI. And then you will get a causal graph like this. You can see that it's entirely different from MLR, those contributions you have seen. For example, this is temperature, and these are different drivers, and these numbers are the lags. For example, if you do not find a lag, that means the relationship is instantaneous. Something happens there, the same time it affects the process. This is, for example, humidity. For example, and this is precipitation or rainfall. It affects temperature. This humidity affects temperature, but there is no direct connection, heat flux and temperature here. Here is the point. You should know what you are doing. And if there is a graph, something like this, we need to explain this. Okay? It gives you a graph whether it makes sense or not. So this is for all 7 temperature homogeneous regions for India, just like I did for the regression. Can we make it afterwards so that you may please note down? Thank you. And you can see that in different regions you have different connections and different relationship. For example, in some regions you have direct connection ENSO and temperature. In some regions you do not have. And some regions you have heat flux connection, and some regions you do not have that direct connections. So what I'm saying is, when you have these graphs, you have to make sure that these graphs have some sense, in physical sense, okay? And whenever you have this humidity and there is no connection with temperature, maybe that's a false relationship, like that. So we published this in this journal. And when you do this for different regions, it is also a test for your code.
Can you go back to the paper?
NPG. And just like data, we also need to test our models. Whether it's causality or anything, you can use different, I use PCMCI for that, but you can also use Pearl causality, Granger, like any other. But you also need to test it. So this is one of the best test beds for your model, whether your physical model or your statistical model. This is the region called third pole. You know that there are 2 poles, north and south, Arctic and Antarctica. And there is another similar kind of region. Similar means it's not very similar, but you have also largest ice mass outside the pole here. That's why it's called third pole. It spans 12 countries in Asia. This is called the water tower of Asia because the largest 10 rivers, if you take in Asia, all are originating from this region. So that means something happens with the ice melt in this region that we are in stake of water. And there will be also floods in these regions. You can see that Indus, Ganges, Brahmaputra, all 3 rivers are shown here. It's also interesting and in the climate point of view, because you have westerlies from this side, so this region is dominated by westerlies. You have East Asian monsoon region here in this region, and you have Indian summer monsoon from this side. And this is the desert region actually, it's completely arid. So this is a very good region for testing your model, your statistical model. So we were looking at what is happening there in all these 4 regions, and we have 4 points, R1, R2, R3, and R4. And you perform the causal analysis with snow melt, melting of snow, how snow melt is impacted by different parameters or different factors, not parameters, different factors. For example, North Atlantic oscillation, Arctic oscillation, these are some climate anomalies. And then you will find that the features, all these different regions have different features, all those features have captured in the causal analysis as well. And there some are instantaneous, and there are some time lags. Time lags are also very important because when you have something, if you are looking at humidity and the temperature connection, and you get a time lag of 4 months, that is not correct. That will not be working. So you have to be very sure about the result as well. So I am not reading about the result. What I want to tell you is you can test your ML model with this kind of different regional analysis, but you also should know, in order to interpret this, you need to know the physics and what is happening there in that region. So this was also published in another paper. And then water vapor. This is the largest greenhouse gas, you know that. One of the biggest reasons for global warming. So here 3 cases are there: Arctic, Antarctica, and tropics. And if you want to look at what is happening in your model, this is another test. For example, here Antarctic. And this is, here you have Antarctic ice as a parameter here. And then you have another one, North Atlantic oscillation, that is in the northern hemisphere. And this is in the southern hemisphere ice. You see that there is no connection between North and Atlantic oscillation or water vapor here. So that means it should not give that you also find in it. On the other hand, you have North Atlantic oscillation here, and that affects that mid-latitude of that region. So it is capturing that feature. And if you look at the tropical region, you know that there you have a lot of water vapor in the tropics. Almost everything affects tropical water vapor, and your model captures that very well as well. So this was also published in another journal. Now we are coming to chemistry. So we were talking about application of ML methods for finding drivers, finding relationships, and how you interpret. If you have a data and there is something anomalous, whether you can interpret something with that models. So this is one of the first papers published in atmospheric chemistry applying ML on surface ozone in Antarctica. We wanted to look at what is happening in Antarctica. This region is very important because, first climate change signals will be emerging in the extreme regions. So if something happening there, you can readily visible. So that is one of the reasons we wanted to go to Arctic or Antarctic or these extreme regions to find whether something is happening there in terms of climate or atmosphere. So this is surface ozone data. So now we are coming to the chemistry, how we can use ML techniques in chemistry for interpretation or making the data. So these are the Central Pollution Control Board measurements in India, different regions. We don't have any measurements in Kashmir. We have only few measurements in Northeast. You have hardly any measurements in the desert region of Northwest. Okay. These are the seasonal distribution. Now, you can use the same kind of regression to interpret things. For example, what is the contribution of meteorology, temperature, precipitation, humidity for changing ozone in a particular region? You can use that. And, but it's chemistry, right? The chemical compounds. There are also chemical reactions. For example, surface ozone is produced by, it's not directly produced, it's produced with NO2 in presence of VOCs, and you also need sunlight. For example, so you also need to have chemistry in it. So one way to interpret this is you can apply this regression, and then you have your measurements, you subtract it, then you will get residual. And then you can say that the residual is from chemistry. Okay. For example, these are the chemical drivers, okay? Biogenic formaldehyde emissions or NO2 emissions, and you can use different meteorological drivers, right from boundary layer height to total cloud cover. And then you use this regression equation, then you can make the data. Just like this, you have the regressed one, MLR fit is red, and you have surface ozone in blue, and the difference is what you interpret as chemistry. Okay? This is one way to do that. But our problem is, as you said earlier, our measurements are sparse. You don't have. And these are not continuous as well. So if you wanted to analyze what is happening in terms of pollution, because surface ozone is very important, it's a greenhouse gas, it warms the atmosphere. And we have found even up to 0.4 degree centigrade, it can warm the atmosphere. And it affects agriculture. It directly affects agriculture because if you have more pollution, your production will be lower. And it also affects health. So its impact is threefold. So that's why this analysis is very important. But we don't have data. This CPCP data are not enough to make an impact study. For example, recently we studied that ozone distribution in India, whether the NCAP, our policy, there is a national a pollution policy is there called NCAP, whether it is working or not. It implemented in 2018, whether we find any reduction in pollution or not. So in order to do that, you need data. You need continuous data. You need data in different regions. Here, one way to do that is you use an ML technique. Okay? So we use this machine learning based approach to make the data, to make a gridded data to all over India. You can also do that with statistics. This is the traditional method, like satellite-based residual correction method. For example, you have ground-based measurements, And if you have satellite measurements, then you take measurements here, interpolate that, and then you can make the Kriging method, simply interpolation, okay? And then you can make the data. This is also weighted by, you can have a Gaussian, and then you weighted interpolation, you do that, and then you will have a calibrated ozone data. That means you have measurements, you have also satellite, you find the difference, you have the residual, and then you do this interpolation, Kriging, and then you add that residual, then you will have the corrected method, bias corrected data. That is one way. But on the other way, using this ML technique, you have different decision. I think we run 1,000 decision trees here. You have trees, nodes, and different combinations, and then you will have that data. Each decision tree is constructed using a random subset of different features, and then you will have the predicted data. Now you see that how different and how good is these data. So this is the Indian map where you have different climate regions here, and this is the residual correction method, the data that you made, and this is with the random forest method. Now you look at the difference in particularly this region. I told you earlier that we do not have any station data in the Northwest. So it overestimated because machine learning, they know that they do not have data, so they have to take the higher side data in this side. But residual correction method, they interpolated, that's a flat interpolation. There is no consideration. This is the advantage of trees. So this data we compared with other measurements, this is much better than this one, but you have to be very careful about this. So you should also know what you are doing and what is there and what is not there as well. So you have to take care of the data very well. So this is the second advantage. You can make data, and these data are important for models because for your model, you need to give gridded data. So this is, sir asked whether you validate it or not. Yes, this is one example for that. We validate, you see this residual correction method, you have load of spread, you can clearly see the spread, but when you use the random forest or machine learning method, you can see that it's not that spread, but the comparison is much better. You can see the R values, it's much closer to 1. So this is one way to apply machine learning tools in these kind of analysis. A part of that was published recently in Environmental Pollution. And today morning, there was a question whether related ocean carbon cycle, whether models are capturing ocean carbon cycle or not. No, because we don't have data. You have buoy measurements here and there for ocean, and we have PCO2 measurement. In oceanic carbon, we call the partial pressure, unit is partial pressure. How much is dissolved in the water. So that is called PCO2. This PCO2 measurement, in Indian Ocean, only one buoy measurement is there in somewhere. But our model doesn't know whether this is oceanography data or carbon dioxide data, atmosphere or ozone or whatever. We just give the data, right? So one way to make the data is, if you do not have data, whether there are first guess data available from models, global models. So we used 16 global models and made a data set. And then this data set we used to cluster. Okay, it's a cluster. Now you have 4 clusters. For example, in this first step, you have 4 clusters, and then you have the predicted data. But you know that this climatology will not work. This carbon dioxide is increasing, and in tandem with that, oceanic carbon cycle is also changing. Ocean acidification is happening. More CO2 is in the water. So you need to add the trend, what is happening in the water. So in order to add the trend term, you find the trend, you add and run again, then you have this final data with interannual variability. Whether you can have the monthly, you can have the season, you can also have the So you have the interannual data. That means every year, every month you have data. Earlier, you had only the monthly data. Okay? So using that method, you can really make a data, monthly data from climatology. So that is one advantage, because you do not have, otherwise you do not have data. Without data, you cannot study as well. So this is another advantage of machine learning techniques, how you can use to predict models and to find the carbon cycle. For this, one of this PhD work is finding the carbon cycle, ocean atmosphere exchange, carbon exchange like that. So this is the available PCO2 measurement in the Indian Ocean. This only the available measurements are there. You can see the huge gaps are there. And with this data, you cannot model. Because these data are not continuous. These are cruise measurements somewhere, some period. For example, 93 you had a cruise and some region you have some like this. These are the cruise. These are not continuous. In some year, some point like that. These data you cannot fed into any model. So we need a data. That's why we did that. And then you can make, with random forest, you can really make a data like this with seasonal signatures in it. And this is using that random forest, we made this data and then used to study the acidification carbon cycle in it. So, and we compared that with available measurements. You know, I forgot to tell you that when you use any machine learning methods, or you train the data, either you can make a 70-30, it's up to you. Most of the time we use 70% for training and 30% for validation. And sometimes in chemistry we take a rigorous, because it's a bit difficult, because chemical species reactions takes place in some in seconds, some in minutes, like that. So you need more training. So we take 80% and 20% for validation. So those regions you do not have measurements, you will definitely have higher bias. So you have to be very careful. You have to map something like this when you interpret. Okay. And just like this, atmospheric science, physics, chemistry, or ocean, and then you can also use that in land science. We tried that whether, for example, the photosynthetic activity or vegetation in India is increasing or not, or if it is increasing, what are the reasons, what are the different drivers, like that. You can apply this kind of causality to any data or any process to interpret or to find or even to predict. So I'm not going to the details of that. Sorry, okay. And then I'm summarizing the summary and the way forward for this. The important thing is the data. Whenever we are talking about model, without data, there is no model. So a good model can only be made with good data. So more data, more information, your interpretation will be more reliable, accurate, and you also need to check the physical connection. You should know what you are doing, and you should be aware of the process. And then these are data-driven models. So I am coming back to this slide here. Data quality is very important. Because your data is not good, then your model is not good. Missing data, you have to take care of the missing data. And there are many gap filling algorithms as well. Data integration is important. And different types of data homogenization, for example. You have temperature data from maybe AWS or automatic weather station from satellite or any other. But how do you integrate it? These are very important. Okay. And what techniques you use? There are good techniques in ML available for integrating data sets, making good data. So data is very important. And then what are the opportunities of future? You can interpret complex models and the processes, and you can analyze even chemistry. And then you can also have real-time data processing. Our biggest problem in climate science, or whatever we do actually, this computing time. If you want to run a model, it takes a lot of time and it's a lot of money as well. So most of the time what we do, we use assumptions. Sometimes we use parameterization. Morning we were talking about that. So parameterizations are very important. When you talk about the climate model uncertainties, the biggest uncertainty is radiation, cloud, and then we don't even know what a cloud is and how it is forming really, and what the structure is. We assume everything. We have some measurements. With respect to some measurements, we are assuming something, and then we are trying to parameterize. So within a grid, if you nest it, it takes a lot of time. It's a lot of computation is you need it. So real-time data processing means it will take more time, more computing power. So some of these ML techniques, if you use, that will reduce the load. That will minimize the loops as well. If you check any global model, climate model, almost all models, even we are using Julia these days, right? But models are in Fortran. Why is that? Because the Fortran loop works better. Now we are changing that. Okay. If you use Python earlier, it was not possible. You can call any language in Python and then you can run. Like only you need a Python code to call MATLAB, IDEAL, or anything. You need only a Python code for that. Earlier it was not possible for us. So just like that, now these Fortran codes will be changing. Maybe some techniques can be incorporated. So those are the opportunities, those are the future. And for policy analysis, this is very important. You need good data. So these techniques are very, very helpful for impact assessment studies. These are very important. Something is happening there and we are also interpreting, but what we can do about is very important in terms of climate change or global warming. So impact assessment studies are very important, but in that aspect, this will be giving a good, clear indication. So, sorry about this trash word. The final thing is, in any model, trash input is trash output. That means data is very important. Data are very important. Thank you very much. And I thank you for this invitation, and I acknowledge my gratitude to all data providers, all algorithm and model teams, students in my lab, and our center head and IIT Kharagpur and funding agencies. Thank you.
Thank you. Thank you, Jayanarayanan. So, questions to him? You want to know?
Okay. Okay, thank you. Yes.
Statistical method you have done. So the Rajasthan and Gujarat region is, the bounds and all physics, there was no data. The same was with J&K, the same was with Northeast. But the way it is interpreted, everywhere the data is not there. So is this the bound of the boundaries or any random data it is picked up?
I showed you the oceanic CO2, not atmospheric, and we do not have data. In Indian Ocean, we have only one buoy data.
No, sir, not that.
You're talking about ozone.
Ozone, okay, sorry.
Ozone.
That's true. We don't have data there.
So he is asking how you filled up that data.
Sir, we did not. We can't. We tried that.
No, but then you go to the next slide, I think. And
This is how I did that. That's what I explained here in this. This is interpolation.
Interpolation fine. Is it the bounds which made this color, to predict it as more over Rajasthan and Gujarat? Is it the bounds? That's what I'm asking.
No, actually, this is the machine learning itself gave this data, but these are not correct. We have not used it. But
Without data, it is interpreting something. Is it the boundary values it is interpreting?
yes.
Random values.
No, not random. These are mostly taken from the boundary. Yes. Yes. Sir.
Now you said that machine learning is on an average giving better results, but if extreme results are worse than the residual method. What do I get as a conclusion from this? The residual method is more accurate, or this is more accurate, or
No, sir. The machine learning itself is accurate.
is more accurate?
Yes.
But it's giving more error, you said in
This is the point I wanted to make, because I made this color red because when we do not have the data in some region, then we should not use that region. It should be very careful. And the first thing is, when we have something, when we make a data, we need to do this first. You have to make sure that you have good result as compared to available data. This is very important.
I think other than just the average value, I think the standard deviation and everything else should be measured as quality of the prediction.
Yes, sir.
And then when you came to that other one, where you used random forest to generate the data,
Yes, sir.
there also did you do a study of how much data
Yes.
You could have reduced it a little. Yeah.
So this is the mean absolute bias. This is bias, this is mean absolute error, and this is R, and this is RMSE.
No, what I'm saying is that you have X amount of data which you are using for
Yes.
generation.
So,
Now, if you reduce that and still try to generate, we want to see whether that accuracy.
it affects, sir. Yes. It matters. Training data matters. That's what I told. We used
How much is enough?
for.
Optimal.
Sir, here we used 500 trees, and 70% we used for training, and 30% for validation. And if you reduce it, these errors are higher. And this is optimum is something like 70. That's why we fixed it.
Okay, so any other questions to you?
Anybody use generative AI for this?
No, sir, no. It's a bit complicated.
So, I think you should thank Professor Jayanarayanan for
Thank you very much. Thank you also for, sir, inviting.